Vancouver High, AP Chemistry. We're in Unit 8, Equilibrium, and this is Lesson 37, Equilibrium Rice Tables. So equilibrium, again, let's just review the concept. Not all reactions go totally from reactants to products. So 100% reactants, and later on at the end you have 100% products. Many reactions stop somewhere in between. They have a balance in between reactants and products, where there are still some reactants left and where there are some products made but not entirely products made. Also, a characteristic of equilibrium reactions is they can move backwards. They can move from products back to reactants. So you could actually start in a situation where you had 100% products and 0% reactants. You start with the finished product. That reaction will actually move backwards. But reversible reactions like that have some balance, some happy place where they would like to stay with a certain amount of reactant, a certain amount of product. And equilibrium studies those situations and how far a reaction wants to go and in which direction. So equilibrium concentrations can be found if at least one reactant or product are known. This is done using a rice table, which is also called an ice table. They are the same things. So a rice or ice table shows initial beginning concentrations, the change in concentration, and the equilibrium and ending concentrations. In a sense, it almost gives you kind of a worksheet format where you fill in the blanks on that table down there. Usually you're given initial concentrations and you're asked to figure out the equilibrium. It involves a little bit of algebra, and that's what you would do. But the idea is to complete that table and then use that to figure out the equilibrium constant or the concentrations of each of the reactants and products. So let's just start off with an example. When 2.0 moles of H2 and 2.0 moles of I2 are mixed in a 1 liter vessel at 430 degrees centigrade, how many moles of HI gas will be present? So there's the reaction down there in the ice table. It's under the reaction line, and it shows you that H2 plus I2 is going to give you 2HI. So they've given you the initial concentrations, what you had at the beginning of the reaction. It was 2 moles of H2 and 2 moles of I2, and if they don't give you anything for the product side, the HI in this case, then you just assume it's 0. So to solve this problem, we will use the rice table to form an algebraic expression for the equilibrium values of H2, I2, and HI. The initial values of H2 and I2 are given. No initial value of the product HI is given, so we assume it is 0. The value of the temperature is not important. It is only important that the temperature remains constant, as in a kinetics problem. So we need to calculate the change and then the equilibrium of each reactant and product. We use the variable x for this unknown. We know that we will consume 1x moles of H2 and I2 and will produce 2x moles of the product HI based on the stoichiometry of the reaction. So the way you set up the change line very, very simply is you have some unknown change. That's the whole point of doing this. You don't know what that change is going to be. That's going to eventually lead you to the equilibrium. But one thing you always do is you always put whatever the coefficient in front of the reactants and products is, you put that in front of x. And on the reactant side, the H2 and the I2, it's a negative 1x because you're decreasing the concentrations of those reactants, and on the right side, the HI, you're increasing the concentration. You know that this reaction initially has to be running from left to right, from H2 and I2, which are reactants, over to HI, which is a product. So it's going to be negative on the reactant side and positive on the products side. So you always write the change line like this. Your x is unknown values, but you know the proportion of moles. It's going to be 2 HI for every 1 I2 for every 1 H2. And so you write those coefficients. So now you can simply add or subtract as is appropriate. So we subtract the change row from initial on the reactant side. We add the change row to the initial on the product side. This produces three algebraic expressions that we can plug into the law of mass action equation to determine the equilibrium values of the reactants and products. So you see down on the equilibrium, you just simply said 2.0 minus 1x, 2.0 minus 1x, and 0 plus 2x. And that gives you your equilibrium, the equilibrium concentrations, at least in algebraic form. Now you solve for x just like you would in an algebraic equation. So the next step is you set up the law of mass action for this reaction, and so it's HI squared because there's a 2 coefficient over 1 H2 times I2, and we figured out in an earlier problem in the previous lesson that for this reaction the equilibrium constant Kc is 50. So that was already calculated in an earlier problem, or if in this case it could have been just been given to you in this problem, but we did calculate that earlier. So now what you do is for those concentrations of H2, I2, and HI, you plug in your algebraic expressions in the equilibrium line. So for HI it's 2x, and then you have to square that. For H2, it's 2 minus 1x, as you see on the bottom under H2 in the equilibrium line, and it's the same for I2, it's 2 minus 1x, and that's going to equal 50. So now what you can do is you can combine the 2 minus 1x times 2 minus 1x on the bottom and call that 2 minus 1x squared. So you end up having a square over a square, 2x squared over 2 minus 1x squared. And now to solve for that, you just take the square root of both sides. Square root of 50 is 7.071, and the square root of the right side is just going to be 2x over 2 minus x. I left off the 1 in front of the x in that case, it's not necessary. So now it just simply becomes an algebraic equation, multiply both sides by 2 minus x, and do whatever you need to do to solve for x, and you end up with x equals 1.6. Okay, so what does that mean? It means that if you go up to the equilibrium line and plug 1.6 in wherever you see x is up there on the equilibrium line, that will tell you the concentration of each of those reactants and products. So we now use the value of x to compute the equilibrium concentration of HI. Concentration of HI is 2x, and we now know that x equals 1.6, so 2 times 1.6 equals 3.2 moles of HI gas. And notice you could also use that 1.6 value for x to figure out the concentrations of H2 and I2. Okay, let's take another example here. We're taking N2O4 and placing it into a reaction vessel at a concentration of 2.5 molar. What is the concentration of NO2 at equilibrium? So you notice the reaction is written as NO2 being the reactant and N2O4 being the final product. But in this reaction, we're not given any NO2, we're assuming it's 0, and we're given only N2O4. So in a reversible reaction, it doesn't matter. This reaction can run backwards. It can run from N2O4 to NO2. What's significant about an equilibrium reaction is it's going to end up at some equilibrium point. Whether you start with all NO2 or all N2O4, it's going to move towards that equilibrium point and settle in at that equilibrium point. So you see the law of mass action down there below. The product is on the top. The reactant, the official reactant, even though there's none of it in the vessel right now, is on the bottom, and you square it because it has a coefficient of 2, and you're given the equilibrium constant in this case of 87.2. That's just given to you, so you don't have to ask where does that come from. It's just a given here. Okay, so there's the Rice table for this reaction. The reactant, you start off with none of the reactant and all of the product. And so this reaction is going to move from right to left. It's going to favor reactants, meaning it's going to move back towards reactants. So all of the initial concentration is the product N2O4. This means that the reaction will move backwards from products to reactants. You might ask the question, why didn't they just write it that way? That N2O4 is the reactant and the product is NO2. Because generally the reaction is written in this fashion, and so we just say, okay, that's fine, it's written from reactants to products, but if you start with all products, the reaction is going to move backwards towards reactants. Okay, so you set up the rice table and you have your initial concentrations on the top, and here are the change. This is the change line. Remember, it's always unknown. That's why you're doing this rice table. So it's some unknown amount x, and you always precede it with the coefficient in the reaction. So in the case of NO2, it's 2. In the case of N2O4, it's 1. And since N2O4 is going to be decreasing in concentration, it's a -1. And since NO2 in this particular reaction is going to be increasing in concentration, it's +2. So the change is the unknown variable x multiplied by the coefficient in front of each reactant or product. In this reaction, it is the reactant that is increasing and the product that is decreasing. Okay, so that's what you would get down on your equilibrium line. 0 plus 2x equals 2x, and 2.5 minus 1x equals 2.5 minus 1x. So those are the equilibrium in algebraic terms. Those are the equilibrium concentrations of the reactant and the product. So now you take your law of mass action and you plug those algebraic expressions into the law of mass action. So for N2O, it should be N2O4. That's going to be 2.5 minus x, and for NO2 it's going to be 2x, but then you square it because it does have that coefficient in front. So notice that the 2 in front of NO2 kind of affects the equation twice. It becomes the coefficient in front of 2x, and because of that 2, you square that particular term. Alright, so this equation can be turned into a quadratic to find the value of x. Now I'll just give you a warning, or not a warning, but just something that's going to happen here is that you're never going to have to do a quadratic in these problems. I'm going to show you in this one case that it is a quadratic, but you're never going to have to do that, and I'll explain that in just a little bit. Okay, so here we go. So there's the equation, and you have 2x squared, which equals 4x. So now you've got to rearrange that so that all of the terms are on the left side of the equation. And if you see in the middle there, 348.8x squared minus x minus 2.5 equals 0, that's the typical equation for a quadratic that you did in integrated math 2. So now you have to use the quadratic equation to solve that. And there you see it's kind of a big mess, but you've done it in math before. And what you get for x is 0.086. So the alternate value for x, by the way, in that quadratic equation is a negative number. And in the real world, in the physical world, you can't have a negative concentration. So what do you do with that number? You just throw it out. It's not included. So you really only have one value for the concentration, and that's the positive value. So now what you can do is take that 0.086 and plug it in for x in the equilibrium line of the ice table. So 2 times 0.086 will give you 0.17 molar. That's your equilibrium concentration of NO2. And 2.5 minus 0.086 will give you, in rounded to 2 significant figures, will give you the concentration for N2O4. And that would be your answer. So we're going to 2 sig fig because of the 2.5 molar up there at the top right of this slide. But let me repeat, you're not going to have to use a quadratic equation in this class, and I'll show you why. So fortunately, there's an easier way to solve the previous problem based on the approximation that can be made when a large and small number are added or subtracted. So let's just take an example of 2 numbers, one that's very large and one that's small, 1,000,000 and 5. If you add 1 million plus 5, you get 1,000,005. Well, you notice you have to go out to the 7th significant figure for that 5 to even appear. So for all practical purposes, 1,000,005 can be approximated as 1 million. So what does that say about the 5? It means you pretty much can ignore it. So since you need to go to the 7th significant figure to see the difference, we could approximate 1,000,005 to equaling 1 million. Now, this is not true with a multiplication. If you multiply 1 million times 5, you get 5 million. there's a significant difference between 1 million and 5 million. So if it's a multiplication of a large number and small number, you can't ignore the small number. But if it's an addition or subtraction of a very large number and a very small number, now what do we mean by large and small? It just means relative to each other, in relation to each other. One is very big and one is very small. So if it's the addition or subtraction, then you can ignore the small number. And you're going to see how that helps us to simplify these equilibrium problems. Okay, so we will return to the law of mass action for the previous problem. If we assume that x is much smaller than 2.5, and I'm just going to tell you, you can pretty much always assume that in these problems, then we can eliminate the x in the numerator, leaving it only as 2.5. So over on the left in red is the law of mass action that we had for the last problem in algebraic form. And you'll notice what we do over on the right there in red is we just get rid of that x. You just assume that 2.5 is much bigger than x. And do you remember what x was from the previous problem? It's 0.086. 0.086 is much smaller than 2.5, and therefore you can eliminate that x. So now you don't have to deal with a quadratic. That's the important thing. So it simply becomes an algebra problem at this point without a quadratic. So now we can solve the equation without using the quadratic equation. This is called the simplifying assumption for equilibrium problems. You can use it in almost any equilibrium problem we do in this class. So you see the equation, how it proceeds. 87.2 over 2 equals 2.5 over 2x squared. You square the 2x squared and multiply both sides by that, and you can just see how the algebra works out. Finally, take the square root of x and you get 0.085. You see that you got pretty close to the answer we got using the quadratic, which is 0.086. The 5% rule states if the percentage difference between the answer, in this case 0.085, and the initial concentration 2.5 is less than 5%, then the simplifying assumption can be used. So we can just calculate if it is less than 5%. So 0.085 over 2.5 times 100% gives you 3.4%. So the simplifying assumption gives an answer differing by less than 5% of the initial concentration, so the assumption can be used. And that's going to be true in every problem that we do. All right, let's do another one. Just keep doing these, and this rice table will become very natural and very easy. You'll start to actually where you can do some of these in your head. Okay, so a closed system initially containing 1 times 10 to the negative 3 molar I2 and 2.0 times 10 to the minus 3 molar H2 at 448 centigrade is allowed to reach equilibrium. Analysis of the equilibrium mixture shows the equilibrium concentration of HI is 1.7 times 10 to the minus 3. Calculate Kc at 448 for this reaction. Again, they use that temperature twice. All they're saying in this case, in this problem, is that temperature doesn't change. So you have a valid problem. All right, so set up the rice table, and they give you two initial concentrations, the initial concentration for H2 and the initial concentration for I2. And then you'll notice for HI, they give you the equilibrium concentration. So you put that number, 1.87 times 10 to the negative third, you put that down in the equilibrium row, not up in the concentration row. You're starting with 0 HI. So now you just fill in the boxes, okay? And this actually makes the problem easier when they give you one of the concentrations as an equilibrium. So you're given two initial concentrations, H2 and I2, and an equilibrium ending concentration of 2 HI. When no initial concentration of the product is given, you can assume that it's 0. In fact, when no initial concentration of either a product or reactant is given, you can assume that it's 0. Okay, so now if we know that we started with 0 concentration of 0 HI and ended up with 1.87, then the change must have been a positive 1.87 times 10 to the minus 3. Now notice what that represents in terms of the variables we've been using in the previous problems. there's a 2 coefficient in front of HI, and there's some amount of change that we've been calling X. So that 1.87 times 10 to the minus 3 represents 2x. It represents a change of positive 2x. So that's useful when we go to figure out what is the change of H2 and I2. So see if you can come up with that. What should be on the change line for H2 and I2? It's a specific number, but how do you calculate that specific number? Okay, and there it is. So if the HI, if there's a 2 in front of the X for the HI column, for the product column, so it's a positive 2X, then in the H2 and I2 columns, the change should be negative X because they only have coefficients of 1 H2, 1 I2. So that would be a negative X. In other words, the numbers that you're going to fill in there, you can actually put specific numbers, as you can see, are going to be half the value of 1.87 times 10 to the minus 3. And since they are reactants that are going down in concentration, it's going to be a negative number. So negative 9.35 times 10 to the minus 3 is 1/2 of 1.87 times 10 to the minus 3. And that's how you calculated that. Now you actually have a number. There's no algebra, no more algebra to be done here. You actually have a number that you can calculate for equilibrium. For H2 and I2, it's 1.0 times 10 to the minus 3 minus 0.935 times 10 to the minus 3. And that will end up giving you 0.065 times 10 to the minus 3 for those two reactants. All right, so now that you know that, you can go ahead and calculate the equilibrium constant. So study those numbers before you go on to the next slide or continue with the video. Okay, and that's where we got those numbers. So we have the concentrations. And that's the answer. Now, if you wanted to figure out the equilibrium constant, Kc, you would go ahead and set up the law of mass action, which would be 2HI over H2 times I2. You would plug in those numbers that you have in the equilibrium line, and that would give you the equilibrium constant for this particular reaction. Again, that constant only applies to this reaction at that specific temperature of 448 degrees centigrade that was given earlier in the problem, in the initial problem. And here we go, we're going to do that. So Kc can be computed by entering the equilibrium concentrations into the law of mass action for the reaction. And there you see it done. And it's just a plug and chug number problem. And you get 51 as your equilibrium constant Kc. Now we're going to talk about something called the reaction quotient. The reaction quotient Q is computed the same way as the equilibrium constant K, except Q is computed using existing, not equilibrium concentrations. So let's kind of put this all into perspective. If you have equilibrium concentrations of a reaction and you plug them into the law of mass action, you'll get the equilibrium constant K. That represents where the equation wants to settle at some particular temperature. Is at K. It wants to have that. So what if you computed the equilibrium constant, but instead of using equilibrium concentrations, you used whatever happens to be the concentration at that particular time. It could be mostly almost all products and very little reactants, or almost all reactants and very little products. Well, you'll get some number that's not exactly K, unless you just happen to hit the equilibrium concentrations exactly. You'll get some number that's not K, and we call that number Q. So the reaction quotient is used to tell which way the reaction will flow. So if Q equals K, if you did happen to just put in exactly equilibrium concentrations, then Q would equal K, and that means the reaction's at equilibrium. It's not going to flow to the right, it's not going to flow to the left. If Q is less than K, then that means you have too much in your denominator of your law of mass action. You have too many reactants for equilibrium, more than that reaction wants at equilibrium. So if Q is less than K, the reaction has excess reactants and will move to the right. It will form products. It will favor products. If Q is greater than 0, then that means the reaction has too many products, too much products. It has excess products, and so it's going to move backwards from right to left and form reactants. It's going to favor reactants. So let's go ahead and do one of these problems here. So the reaction for the previous example, and we already figured out that the equilibrium, well, that'll be given to you here. All right, so we're going to use the same values for H2 and I2. The reactants are the same as the previous value, but we're going to pick a different value for HI, for the concentration of HI. We're going to pick 2.5 times 10 to the minus 3. And if you'll remember from the previous problem, the equilibrium concentration was 1.87 times 10 to the minus 3. So you can see that this concentration of HI is greater than the equilibrium concentration of HI. So this product concentration is larger than the previous equilibrium value, so we should expect the reaction to flow backwards from products back to reactants because it has too much product. It has too much product for the amount of reactant. It has the same number of reactants as at equilibrium, but it has more product than at equilibrium, so it's going to want to undo those products and move backwards towards reactants. So you compute Q the same way as Kc. So there we go. We're doing it. We're computing it just like we did at the end of the last problem to compute Kc. And what you end up with is Q equals 90. Since Q is greater than Kc, remember Kc was 51 from the previous example, the reaction will move in the reverse direction to reduce products and create more reactants. So that's all the Q value is. It's basically computed the same way as an equilibrium constant, except you do it with whatever your current concentrations are, not the equilibrium concentrations. Okay, Le Chatelier's principle. Le Chatelier's principle states if a chemical system at equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium so that it counteracts the effect of this disturbance. In other words, it wants to put itself back in equilibrium. If the reaction changes so that more products are formed, it is said to favor products. If the reaction changes so that more reactants are formed, it is said to favor reactants. Okay, so here are some examples. If reactants are added or products are removed, the reaction will move towards products and the change in concentration. So just think about that. H2 plus I2 gives you 2HI, and let's assume that we had the equilibrium concentrations of the reactants and products that we showed in the earlier example. If we add more H2 or I2, it doesn't have to be both, but if we add more H2 or I2 to this reaction, it's going to want to move to the right. It's going to want to form more products, more HI. Similarly, if we're in equilibrium and suddenly we remove some of the HI from our container, it won't have as much HI as it needs to have in equilibrium. So similarly, the H2 and I2 will combine to form more product, more HI. It can also go in the other direction. If reactants are removed, that would be H2 or I2, or products are added, that would be the HI. The reaction will move towards reactants, that is backwards. So it will favor the reactants. So if we're in equilibrium and all of a sudden we put more HI into our container than the equation likes at equilibrium, then that equation is going to move backwards. It's going to decompose that HI into H2 and I2 gas. Similarly, if we're in equilibrium and we remove H2 and I2 gas, then the chamber, the container, doesn't have as much H2 and I2 as it would like to have at equilibrium. So again, it decomposes the HI to produce H2 and I2 gas until it's back in equilibrium. This goes back to our classroom example that we gave in the previous lesson. If you have 12 students in one room and 7 students in another room, and everybody's happy, everybody's comfortable, and suddenly you put more students into one of the rooms, let's say the room with 7 students, there are going to be more students than there want to be there at equilibrium, so some students are going to flow over to the 12 student room. It could go the other direction too. If you put more students in the 12-student room, they'd want to flow over to the 7-student room. So it's just that same kind of concept. They want to get back into balance if you throw them out of balance by either adding or subtracting reactants or products. So you add H2 or I2 and you remove HI, then that's going to favor products. It's going to move to the right. If you remove H2 or I2 or add HI, that's going to favor reactants. It's going to move to the left. Okay, now heat can also have an effect. In endothermic reactions, heat is treated as a reactant. Think about that. Endothermic means that to cause the reaction to go forward, you need to put heat into it. Heat goes in. So heat is treated as a reactant. You have to add heat in order to make the reaction take place. So heat added pushes the reaction to favor products. It pushes the reaction to the right if I add heat, because heat in an endothermic reaction, that's a plus delta H reaction, is treated as a reactant, so you need it in order to make the reaction go from left to right. In endothermic reactions, heat is treated as a reactant, so heat removed pushes the reaction in favor of reactants. Think about that one a little bit. That might not be quite as obvious. You need heat to make the reaction go. That means putting heat in will cause it to go from left over to the right. So if it reasons that if you take heat out, the reaction will move backwards. It will move from products back to reactants because you're removing a heat from a reaction that needs heat in order to move from left to right. So removing heat will cause the reaction to move backwards from right back to left. So that's going to favor the reactants. How about an exothermic reaction? In an exothermic reaction, heat is treated as a product. It comes out of the reaction. So heat removed pushes the reaction in favor of products. So heat wants to come out of that reaction. So think about this. Heat is coming out. It's kind of building up. If you can remove the heat, say by putting a fan on that reaction, it's going to cause the reaction to go faster. Heat's coming out. You're removing the heat. And so it's causing the reaction to go from left to right. It's causing the reaction to favor products, to move from left to right. In an exothermic reaction, heat is treated as a product. It's coming out. So heat added makes the reaction more difficult. It makes it more difficult for heat to exit and pushes the reaction in favor of reactants. Again, this one might not be quite as obvious, but heat is trying to come out of this reaction. But you're doing just the opposite. You're shoving heat into this reaction. You're turning up the temperature in the room. That's going to make it harder for the reaction to run from left to right, from reactants to products. So if you're adding heat to a reaction that's trying to get rid of heat, you're going to slow it down. You're going to even move it backwards from HI back to H2 and to I2. So putting heat into an exothermic reaction is going to favor reactants. Okay, now we're going to deal with how does a pressure increase or decrease affect the reaction. If it's caused by volume for gases only, the reaction below has 1 mole on the reactant side, the N2O4, and 2 moles on the product side. So an increase in pressure favors the side with fewer moles. Why? Because it's trying to reduce. If you increase the pressure, it's trying to reduce the pressure to get back to equilibrium. It wants to get back to where it was before. So how does it reduce the pressure? It decreases the number of molecules, of moles, that are in the vessel, in the container. So think about that for a second. You increase the pressure, it wants to decrease the pressure. You can decrease pressure, if you remember PV equals nRT. If number of moles goes down, then pressure goes down. So you can reduce the pressure back to equilibrium by reducing the number of moles. And the way this chemical reaction would do that is by converting 2 moles of NO2 back to 1 mole of N2O4. That would reduce the number of moles and would reduce the pressure. If you decrease the pressure, it does the opposite. It wants to increase the pressure So it does that by increasing the number of moles in the container, the number of molecules in the container. So it does that by moving to the right, by moving from 1 mole of N2O4 to 2 moles of NO2. So PV equals nRT. Increased P increases the side with fewer moles. Decreasing P increases the side with more moles. So if pressure is increased, the reaction will try to return to equilibrium by reducing the number of moles, which will reduce the pressure. This can be done by turning products back into reactants in the reaction above. That will reduce the number of moles, going from right to left. If pressure is decreased, the reaction will try to return to equilibrium by increasing the number of moles, which will increase the pressure. So it'll get it back to equilibrium pressure. This can be done by turning reactants into products. 1 mole of N2O4 to 2 moles of NO2 in the reaction above. Okay, finally, catalysts. Equilibrium exists when the rate of the forward and reverse reactions are equal. This will happen at a particular activation energy represented by the highest point in the reaction pathway. So we talked about this when we were talking about kinetics. We talked briefly about catalysts. When a catalyst is used, the activation energy of the reaction is lowered. Lowering the activation energy increases the rate at which reactants are converted to products, but not the amount of reactants and products. So here's the key point. Catalysts do not change the value of the equilibrium constant. They'll cause a reaction to speed up, but even though the reaction's running faster, it's still going to reach the same equilibrium as if there was no catalyst. So how fast a reaction goes and how far it goes from reactants to products are not related to each other. It can go very fast and reach equilibrium, or it can go very slow and reach that exact same equilibrium. So the catalyst increases the speed of the reaction, but it doesn't change where the equilibrium is for that reaction. Alright, so that does it for this lesson on equilibrium. There's one more related topic called solubility product. We're going to do that at a later time, but this will give you enough of an understanding of equilibrium to move into acids and bases this week and next. And so be sure you understand this. Get this lesson done as quickly as possible so that you're ready to go into the acids and base reactions that will deal with this concept as well. Okay, we'll see you in class.